We got into this a little bit at the end of the previous video, but when we make up a thermodynamic model from scratch or pull it out of our back pocket or whatever and do the processes, the derivatives that get us the equations of state, the response functions, it's not necessarily true that any random thermodynamic potential model we choose gives us sensible answers for those equations of state and those response functions. So it's good to be aware that there are certain conditions that must be satisfied by a thermodynamic model in order for it to make sense, in order for it to give predictions that are not obviously wrong at the outset. So here are three predictions. Here are two conditions that are based off of state variables. When we are given a certain potential, we can take derivatives of that to get formulas for the state variables, for the equations of state. And many of these state variables have to have a positive or a negative sign. Let's think. If we're talking about the pressure of a physical system, in order for that system to exist in that parameter range, the pressure must be positive. So it must be positive for any physical situation. Now it's possible for the model to predict a negative pressure in a certain range of temperatures or volumes. And what that means is that it doesn't mean the whole model is wrong, but it means that the model is not matching up with any physical state in that region of parameters. So there are a number of other quantities which must be positive to represent a physical situation. Entropy must be positive, right? We know entropy is the logarithm of multiplicity, and a multiplicity is at least one. There's at least one state for every realistic microstate. So the entropy must be positive. If we work, with the Gibbs free energy, where we derive the formula for volume by a derivative, the volume must come out to be positive. We can assume that the number of particles in a system must also be positive. And, of course, when we work with absolute temperatures, we expect they will always be positive as well. So most of these state variables have to be positive. The one that escapes this constraint is chemical potential. We know that the chemical potential can be positive or negative. It's not constrained at all. So those are some constraints on the first derivatives of a thermodynamic system. So let's work out what these actually correspond to in terms of the potentials. All right, let's work on the Gibbs for energy first. So dg dp. Well, this derivative is equal to the volume. The volume must be greater than 0. So the Gibbs for energy, plotted as a function of pressure, must be sloping upwards in order to represent a physical situation. This is at a specific temperature and particle number. What about the variation of Gibbs free energy with temperature? Well, this derivative is equal to the opposite of the entropy. It's equal to negative S. So to represent a physical situation, this derivative must be negative itself, so that when we have the other negative from the relationship, we get a positive entropy. The derivative of Gibbs free energy with respect to N gives us chemical potential, which has no restrictions. Let's write this out for the Helmholtz free energy. the derivative of Helmholtz energy with respect to volume is equal to the opposite of the pressure. So to represent a physical situation, this derivative must be negative. After we do the derivative, we get a negative value, we multiply it by the negative from the identity, and then we get the positive pressure. For the derivative of F with respect to temperature, that gives us also the opposite of the entropy, so this must also be 0, less than 0. All right, so the Helmholtz free energy must slope down in a graph versus volume, and it must slope down in a graph of F versus temperature to represent a physical situation. Again, it's possible that there are regions where these things slope upwards, but those regions of temperature and particle number then could not represent a realistic, physically accessible state. These are the ones that we're going to use most often. We can derive relationships like this on the derivatives for enthalpy and internal energy, but I'll leave those as an exercise. We just look at the derivative relationship and decide whether that quantity has to be positive or negative. Okay, we also have conditions for stability that are based off of the response functions. First, let's talk about the heat capacities. In order for a system to be stable now, the heat capacities must be positive. Why is that the case? Well, a heat capacity represents how temperature and added heat are related. And the second law of thermodynamics tells us that heat flows from hot temperature into cold temperature. If a system had a negative heat capacity, then as heat flowed in, its temperature would decrease, allowing it to become even more attractive for more heat to flow in. So that sort of system can never be in a stable equilibrium. Its temperature goes away from equilibrium as the heat flows. So for a system to be in a physically stable state, these heat capacities must be positive. This means that since these were related to second derivatives of the free energies, that these free energies must have a certain sign of concavity to represent a stable, accessible physical system. So the second derivative of G with respect to T, what is that? Well, the first derivative was negative of the entropy. So dg dt is negative entropy. And ds dt is equal to the heat capacity at constant pressure over temperature. So for Gibbs, these are at constant pressure. Okay, so temperature is always positive. Heat capacity must also always be positive for a stability condition. So since there's a minus sign here, then this quantity must be less than or equal to 0. Right. So our concavity of the Gibbs free energy with respect to temperature must be essentially less than 0 in order for the system to be stable. The other heat capacity at constant volume, so this rule here is derived from Cp. This rule here is derived from considering the constant volume heat capacity. So again, for the constant volume heat capacity to be positive, similar arguments apply, and the second derivative of the Helmholtz free energy must be negative. So when we're looking at proposed thermodynamic models, for the Gibbs free energy or the Helmholtz free energy, if we plot them versus temperature, they need to be sloping down, and they need to both be concave down. So a stable situation for Gibbs free energy looks like this: sloping down and concave down when plotted versus temperature. For Helmholtz free energy, you get the same thing: sloping down and concave down. If there is a region where it's concave up, or if it slopes up during some region, that doesn't mean the entire model is wrong. It just means that temperature range is not a realistic physical state. Let's look at the other variable then. For Gibbs free energy, it will be pressure, and for Helmholtz, it will be volume. So the second derivative of the Gibbs free energy with respect to pressure, this would be equal to dV dP, and the derivative of volume with respect to pressure was equal to negative of the volume times the compressibility, kappa. How does the compressibility, kappa, influence the stability of the system? The compressibility must be positive. If we make the system shrink into a smaller volume, then its pressure must increase to oppose that. If the pressure drops while we compress it, then it's possible for the system to just shrink down to an infinite density on its own. That's unphysical. Or at least it indicates a stability. So this second derivative here, since kappa must be positive, the second derivative of Gibbs free energy with respect to pressure must also be negative. Let's summarize the conditions of stability for the Gibbs free energy. The derivative of Gibbs free energy with respect to temperature must be negative. This comes from the fact that the entropy of a system must be positive. The second derivative of the Gibbs free energy with respect to temperature must also be negative. This comes from the fact that the heat's capacity at constant pressure must be positive. So a graph of Gibbs free energy versus temperature must always be sloping down and must be concave down. So anything like this is allowed. For variations of pressure, the derivative of Gibbs with respect to pressure must be positive. This comes from the fact that the volume of a system must also be positive. And the second derivative of the Gibbs free energy with respect to pressure must be negative. This comes from the fact that the isothermal compressibility of a system must be positive. Putting these two together means that a plot of the Gibbs free energy versus pressure must be sloping up and must be concave down. Any other shape besides this would be an unstable system. Finally, if we look at the mixed derivative, first with respect to pressure and then with respect to temperature, or the other way around, we see this is related to the coefficient of thermal expansion. And this second derivative doesn't have any specific constraint on its sign. So this is allowed to have any sign. And the system will still be stable. What this means is that the coefficient of thermal expansion doesn't necessarily need to be positive or negative. Normally, things grow as they become hotter, but some things might grow as they become colder. For example, water turning into ice. For the Helmholtz free energy, the derivative with respect to temperature must be negative to keep the entropy positive again. The second derivative with respect to temperature must also be negative to make sure that the heat capacity at constant volume is positive. With respect to volume, its derivative must be negative. This is to ensure that the pressure of the system is positive. And its second derivative with respect to volume must be positive. This is to ensure that the isothermal compressibility is positive. The mixed derivative, first with temperature and then with volume, can be turned into the derivative of pressure with respect to temperature, with a minus sign in front. By using one of the identities of exact differentials, we find out that this is equal to the thermal expansion coefficient divided by the compressibility. The compressibility was already seen to be positive, and we know that the thermal expansion coefficient can take on any sign. So this mixed derivative is, again, not restricted to have a specific sign. So for graphs of the Helmholtz free energy versus temperature, for stability, we have to see a slope down and concave down. For the graph of Helmholtz energy versus volume, here we must see a negative slope, but a positive concavity. Anything besides these would indicate an instability in that thermodynamic model. The way these conditions are normally used is to look at a proposed model and decide if it ever has a chance of making physical sense before going into all the derivations. Here's a nice proposed model for the Helmholtz free energy. It has one parameter, A. It's equal to n squared times t squared over v. So it's got the right scaling, it's got the right natural variables, but does it make any sensible predictions or not? Let's check. First, I'll do the derivative of f with respect to v. This gives us negative a n squared t squared over v squared. This derivative must be negative for a model to have a positive pressure. So that is less than 0, and that is good. Let's check the second derivative. This is going to be equal to 2a(n squared t squared over v cubed. That's positive. And this had to be positive to give the system the right compressibility. So that's good also. So this model is mechanically stable. If we plotted f versus v, it would look something like this, which matches what we drew on the general slide before. Now let's check the thermal stability, df dt. This is going to be 2a(n squared t over v, and that is positive. And that's a problem, because this derivative needs to be negative to have a positive entropy in the system. So this model doesn't make sense even for having a positive entropy, and it must be modified in some way to make it work. One possible modification might be to naively look at this and say, oh, I wanted this quantity to be negative. Well, why don't we just make the constant a be negative, or put a negative sign in front of the model? Well, that makes this derivative come right, but it changes the sign up here and makes it wrong. So in this model, no matter what the value of a is, positive or negative, it's always going to have either a negative entropy or a negative pressure, which are totally unphysical. So this model is basically dead in the water. Here's another model that we can check, this time using the Gibbs free energy. First, let's check the dependence on pressure. The derivative of g with respect to pressure is 2bn over p cubed. If the constant b is positive, then this is positive as well. And we've got a positive volume in the system. So that checks out. That satisfies the conditions. The second derivative is minus 6 bn over p to the fourth. That would be negative, which also satisfies the condition for mechanical stability. So let's look now at the derivatives with respect to temperature. dg dt is minus 3a nt squared. That is less than 0 if the constant a is positive. So that gives us the correct sign for that quantity. That's supposed to be related to the entropy. So the entropy is positive in this model. And our second derivative is negative 6 times a times n times t. And that is also negative, which it has to be to give the model a positive heat capacity. So this model satisfies all the conditions of stability and positivity to make it a sensible thermodynamic model. It still remains to be determined whether the constants a and b could be chosen to make this match any realistic system and give good predictions.